So we are.
All right, so I guess we should start, right?
Can you duplicate some stuff there?
Sorry?
These okay, and turn up the volume. Just move these up.
Where is this here? Okay.
Thank you.
Right. So let's start. And we're going to have a very intimate presentation this time, but that's fine. So my name is Vlad, and I'm leading the Toronto R&D Center for VastData. I joined Vast in 2017. It's been a while. And actually, I was employee number 10 of the company. And since then, I've been acting in different roles as architect, tech lead manager, all of that. And Mickey is joining me.
Hi, everyone. I'm Mickey. I am joined the company in about a year ago, a little bit more than a year ago, from academia. I was previously a professor of computer science at York and Toronto, University of Toronto. And now I joined the company as a senior software engineer, and I like building stuff.
Good. All right. So what we're going to talk about today is the VastData platform, which is our main product. And it is a unified platform for streaming, storing, processing, querying, enriching, indexing, all types of structured and unstructured data. And the platform was built from the get-go to be very scalable, and it is built for the exabyte scale. And it is very suitable for modern AI-oriented cases, but not only, as we will see. What we will do, we'll describe the architecture of the platform, the main concepts, and then Mikhail will actually take us for a deep dive into more database-oriented stuff. And that is not a coincidence because databases is what we are working on in our R&D center in the Toronto area. Right.
I'll add one more thing. We have a lot of time, so any questions that you have, just stop us and ask.
Yeah.
I think that will be the best thing to do.
Yeah, it will be more like the discussion and because it's so intimate, so we have time and we have. All right, but first let me present the company. So the company was founded in 2016. I joined the year after it was founded. And in terms of like revenue and valuation, we are one of the fastest growing infrastructure companies in the world today. And now we have more than 1,300 people, employees around the world. And our last formal valuation was 2 years ago. It stood at $9.1 billion. And there are persistent rumors and publications that it has tripled since. And the company has been self-sustained, cash flow positive. So we are not a startup that burns money. We're actually generating revenue. And that's it. In terms of the customer base, so we have some logos here, and they're pretty diverse, and they're coming from all kinds of like use cases and industries, including like neoclouds, AI companies, HPC research centers, universities, hedge funds, and so on. I will name a couple of the more curious ones, in my opinion. So one of them is XAI. Elon Musk's XAI. They have the Colossus GPU supercomputer. I think it's 100,000 GPUs, maybe already a little bit more. And it's using Vast as the data foundation. For all their activities, I think one of the major main one is training Grok. But I guess that not only. Another one is CoreWeave. CoreWeave is said to be the largest neocloud. Neocloud is, so you have the hyperscalers like AWS, Azure, GCP. They're like the classical clouds. Neoclouds are the clouds that provide similar services, but with exclusive focus on AI training, GPU-oriented stuff. And now the hyperscalers are trying to catch up, but still CoreWeave are the largest neocloud in the world today. And relatively recently, it was announced that they signed a $1.2 billion deal with Vast. And if we're looking closer to Canada, we have both University of Waterloo and University of Toronto. They are our customers indirectly via the Sign It for SHARCNET initiatives. So this is like one of the data centers. I think it's in the GTA area somewhere. Okay. And again, this is only like a small sample. Even the logos that I showed you before, it's only a small sample of the actual customer base that we have. And if you have any questions, feel free to stop. So
the question is, can go back to that? So this device is for Waterloo and Dell. So what's the business purpose for this?
So in this specific case, they are going to use Vast as, and I will actually maybe let me present the product, and then we can get back to your question, if that makes sense. Okay. So what is our product? What is the data platform? What is this thing? It's a unified platform that has three pillars. Each of the pillars of the product can be a self-contained product, but they are designed and meant to be used together. Okay, and what are these pillars? So the first thing is what we call the DataStore. DataStore is the storage layer. Generally speaking, it's a full-blown enterprise distributed storage solution that can scale, again, infinitely to exabyte scale, and we have deployments with hundreds of petabytes of capacity. And it has all the advanced features that you can think of if you were using a similar solution in the past: quotas, replication, snapshots, multi-protocol access, so it can serve both as a network-attached storage, like an FS server, but it also can serve as an object store, like S3 server, or a block storage, all these things together. The second pillar is the database. So it's it's a hugely scalable analytical and vector database, which also supports transactionality, inherently supports transactionality. And it is also integrated with a Kafka-compatible event broker. So you can stream events into the platform and get them as tables, columnar-based tables, which you can immediately query. So that's the second part. And the third part is the data engine. And the data engine, as you saw, many of our customers are actually deploying our system on premises, not in the cloud. They're actually deploying on their data centers. So the data engine is basically an orchestration mechanism. So you can build processing pipelines on-prem. Our system can be connected to an external Kubernetes cluster, customer-provided Kubernetes cluster, or it can also host Kubernetes cluster on our compute nodes. And then you can build a pipeline. For example, you can build something like a RAG, augmented retrieval pipeline, so you can shove documents into the system, and you can set up a pipeline which, upon document ingestion, will trigger a function, and that function will process the document, extract its vector embeddings, index the document into the analytical database and the vector database. And then when you have a model that needs to be able to perform similarity search in order to answer your questions, then you have everything already indexed and ready for that. So that's like, it's a simple but important example. Of course, things in practice are much more complex, but this is like the idea of how all the three pillars can work together. Okay, so now going back to your question, the universities currently are using our solution as a data store. Specifically as an FS server, which has a huge scalability and a very good performance profile. So that's what they're looking for, and that's what we are providing.
Oh, how large of a size of data? It should be really large,
right? So our smallest system is probably in the hundreds of terabytes, let's say 300 terabytes. And from there, we can scale to, again, we have customers who probably have like 400 petabytes in a single system, and you can go.
Is that for?
No.
Or from
No. It's not only for backup. And that is an excellent question. So let's talk about it. Like yes, sorry.
Like AWS storage, like what is cost?
AWS S3. Are you familiar with AWS S3?
Yeah.
So we can be an S3 server.
Oh, okay.
And but we also can be at the same time. When I say multi-protocol, it means that at the same time you can access the same data using like NFS, which is like network file system. The same data exactly. So you can ingest it as NFS or S3 and then read it as NFS or S3. That's, yes.
I still have a question. Can go back then?
Sure.
You have this platform including three things.
Yes.
What's the relationship between the three things? Are they totally separate for each other or have some connections?
So again, in terms of, I will keep this slide.
Yeah.
But in terms of basically what is it is a unified platform. So there are connections between the pillars in terms of how you, for example, how you govern access control, in what is like coherency guarantees, how you handle lifecycle retention, and the data engine. If you build a pipeline, it has full access both to the events that are generated there and to the actual data, and it has full access to the database.
And I just want to add one more thing. When we get to my part of the talk, some of the things I'll show is how when we build the database, which is in theory using the data store, we're actually able, because they're interconnected, we're actually able to exploit and put things inside the data store because we have full control of the entire system. And I'll show you at least one example like that.
And again, these things can be used separately, specifically data store and database. DataEngine is a little bit maybe makes less sense, but they also can be used together. That's the point. That's why the system was designed this way.
That drives the platform.
That's the platform, yes. And I have this slide here, which says that like why would anyone need a unified platform for structured and unstructured data, for data store and database? How does it make sense? And to your question, is it like isn't it an archive solution? So if we are looking at estimates, most of the data, if we're looking capacity-wise, in the world is unstructured data, obviously. These are files, video clips, audio clips, pictures, sensor data, you name it. They have by far the larger capacity. They're like 90%, maybe more, of the world's data. And the structured data is a much smaller fraction of the total data existing in the world, and it makes sense. And historically, for organizations, they were relying a lot on the structured side of the data because it is smaller, it is easier to store, it is easier to operate on. But when we're looking at the modern use cases, including, for example, the retrieval augmented, the RAG use case, we understand that in modern use cases, it doesn't make sense anymore to archive the unstructured data. So historically, organizations would store the unstructured data on slower tiers or even archive it and store the structured data on a hot tier. But it doesn't make sense anymore because for many workflows, there is a strong requirement for fast access to all of the data, structured and unstructured. And in a sense, and in these use cases, what users actually want, they want to have their unstructured data readily available, but they need a catalog. Because if you have unstructured data, but you don't know what you have and how to find it, and it's useless for you. So this catalog is actually a database. So that's exactly the rationale behind building a unified platform, because from our perspective, both representations are actually representation of the same data. So you have the unstructured data and the structured data. These are just like different ways to look at the same thing. And then, yes, then you are getting unified, like, for example, tenancy, access control, retention, and so on. All right, so let's start talking about the architecture, and let's start at the very basic layer, and then we'll climb up. So our system is the most, like the foundational architecture of our system is called disaggregated shared everything, or DASE for short, because it's so easy to say disaggregated shared everything. And it came to replace an older existing veteran architecture that is called shared nothing. And shared nothing is something that says Google. I don't think whether Google were really the first one to propose it, but they like promoted it, and it's actually a pretty good architecture, and but it has scalability issues, right? And let's understand what is shared nothing. So shared nothing says, okay, we want to build a system that can scale, so we'll build it from symmetrical, identical nodes. Each node has some CPU resources, memory, and it has direct attached storage, okay? And each node is in charge. So if we're looking at some logical address space of the system, let's say it's a file system. So each node is in charge and has exclusive responsibility at a given time for a given part of the address space. Yes. So that's exactly what I'm describing now. Shared nothing means that each node is responsible for a part of the address space. Let's say we are talking about a single file. For simplicity, this file has an infinite address space.
Privacy, so not leaking the information?
No, not in terms of privacy, but in terms of processing I/O and performing all the background operations like garbage collection, compaction, all these things. So in shared nothing, each node is in charge of a certain piece of the logical address space, and others are not. So they share nothing. That's why it's called share nothing. And this piece of the logical address space, it's called shard. It's like shared, but without the E, so it's a shard.
So it should be independent server.
It's an independent server. And if you want to scale the system, you are adding more. These boxes, you are adding more and more. So they're independent, but not really, because from the user perspective, they are still a single system. So they must know things about each other. Even though I am not responsible for other shards, I must know things about other shards, because some operations will be across shards. Some of the requests that will be coming to me, I will need to redirect them to other servers and so on. And that's why you see these arrows of east-west traffic. So this system has a fair amount of east-west traffic. And that's exactly its weakness, because when you scale it to the multi-100 petabyte scale and you have thousands of these nodes, if they all need to communicate with each other, at some point this thing just breaks. Another weakness of this architecture is the failure recovery, because in order to be able to serve the requests, each node, because it's, again, responsible for its piece, but it has to know a lot of information about its neighbors. Upon recovery, upon turning on, it has to rebuild this state, and this state is non-trivial, which means that failures here are becoming an issue. And again, as you scale the system, failures are becoming more frequent, and things just don't work. So what is shared everything, on the other hand? Shared everything says, okay, we'll actually disaggregate the persistent state and the compute logic. Okay, so we have two types of nodes. We don't have single type of symmetrical nodes. We have two types of nodes. So on the bottom side, you have the data nodes. The data nodes, they're very dumb, because their only function is to expose the devices that are attached to them to the network. They don't have any business logic, roughly speaking. And on the top, you can see the compute nodes, the C nodes. So these guys, we call them D nodes. These guys, we call them C nodes. The compute nodes actually implement all the business logic, right? But they don't have a long-living or persistent state by themselves, right? All the persistent state is accessed over the network, over the fabric, okay? So, and then this means that actually they don't need to talk to each other. There's no east-west traffic. They're only talking to the D nodes. And when this thing, one of the nodes fails, it doesn't have any complex state. So we can just bring it back up and everything works the same way as before the failure. So this thing is much more scalable. And what allowed us to design the architecture in this way is actually, and actually C nodes, they like in a sense rely much less on even on their memory, right? Because they can't have a complex in-memory state, in a sense. And there are two technologies that allowed us to build this start building this back in 2016 and finish building like the basic architecture around 2019. The first one is the RDMA NVMe over Fabric. So NVMe over Fabric allows the compute nodes to have abstraction of local access to remote devices. So from their perspective, each of these drives here is actually a device in their Linux operating system. So they have local access. Of course, it is a little, or depending on the network, less efficient than actual local disk access, but from a like architectural perspective and from the software perspective, it looks exactly the same. Now, the thing that this thing relies on RDMA, which is remote direct memory access, it also means that the CPU overhead of both sides of the compute node and the data node when performing I/O are minimized, and the latency is minimized. So just to give you an idea, over the network access to the device.
Now, I have a question.
Yes.
From my understanding, this is like a distributed database, right? So each
Sure.
of the nodes should be connected with a network. I
Sure.
think it's not some common use network. It should be the high-speed network.
It is a high-speed network. That's true. It's so when we started, it was, I think it was already like 100 gigabit, and today it's probably also going to like the 400 gigabit links.
So it must be deployed in. It cannot be deployed on the internet. Right? It must be deployed on the local.
It's a local cluster.
Local connection.
Yes, having said that, we do have a cloud offering where we actually simulate this thing in some sense.
The cloud.
And in the cloud, you will not have RDMA, you will have TCP, and the performance will be worse, but the system will still operate.
Another thing we have is we can have multiple clusters connecting to each other with a single globe, acting as if they are a single global cluster in some way.
Okay.
But yes, the network, the C nodes and the D nodes, they're of one cluster or in the same physical, data center, and maybe there's another cluster somewhere else. But yeah, it's very fast.
Yeah. Well, like you don't have to know that. There's two different clusters. You're just interacting with.
Yes.
Seems like one.
Yes, obviously there is the speed of light and there are some physical constraints, but yes, from the abstraction perspective, you are.
It's a home machine. I don't know the details. Let's say the home machine.
Yeah.
Yes. Yeah. And another technology that was very relevant for us, which actually somehow I think connects to some of your work maybe. So the non-volatile memory was coming to the market around the same time. We don't use it as a non-volatile memory per se in the compute nodes because this goes against the principle of our architecture of not having persistent state. But we use its slightly slower cousin called the SCM, storage class memory. So some of these devices are actually, so most of the capacity, like 95% of the capacity is QLC flash, the cheapest flash that we can get. But the another 5, maybe 4, maybe 3% of the capacity are actually SCM drives, which are also NVMe over Fabric accessible. Okay, and why do we need these things? Because we do want to have something that is as close to persistent memory, so that when the I/O comes to a C node, the C node can immediately persist it, right? And we don't want to persist it into a QLC flash. We want something that is faster, that can sustain a very small I/O and have a very high endurance. And SCM is like the perfect fit for this thing. So these two technologies allowed us to build the system in this way. And the shared everything, it also opened a lot of possibilities for us in terms of erasure coding, because now we can do erasure coding across data boxes. And we can do a global similarity compression, which means that we can have higher data reduction rate because each of the nodes sees all of the data because it's not SHARCNET. All right, so let's mention a couple more things. So when a client, it can be the file system client or database client, when it has to access the system, it can actually access any of the C nodes, right? Because the state is shared. And actually what we do often, we'll do a kind of like a DNS round robin or something to load balance between the C nodes, but it's transparent to the client. So from the client perspective, it has a pool of IP addresses, and then it can just use any of them for access for any of the protocols and the database. Okay, and then the C node will access the relevant data, and the data can come from any of the data box. All right. As I mentioned, the C nodes do not need to talk to each other, so there is not much or at all east-west traffic. The storage you mentioned, it's easy to scale and extend. You can add more capacity or more compute independently. It depends, like the ratio is up to you. And you can also build heterogeneous clusters. So you can mix different generations of hardware in the same system, and you have a way to balance the load. Fast failure recovery, because CNOs don't have any long living state. And that's it. So that was DASE. Again, I don't think that we invented it. Probably many people at the same time are thinking about similar ideas, and I know for sure that today there are probably other vendors with other systems that are building it the same way. But back in the day, it was like a new thing, and it allowed us to build a system that is very, very scalable. All right, let's talk about another fundamental thing in our architecture. So I mentioned that we can act as a block storage, as a file system, as an object storage, as a database, as an event broker. So how does it work? Like, what is this magic? How come the same system can do all these things? And the answer is that internally we have a unified layer, which we call the element store, right? And the element store implements this thing called the element. Okay, so like everything in Linux is a file, everything in Vast, if you look underneath, is actually an element. Now, all the elements share a similar structure. Their metadata is stored in the SCM, and their data is stored in the QLC flash. They are based on a B-tree, as I will show in a moment. But they come in different layers. So one of the elements can be a table, another can be a directory, a third one can be a file object or something that is like file-like, and so on. And the API of this layer is flexible enough to allow us to build more and more abstractions on the same foundation. Yeah, so that's the second fundamental thing about the architecture. And if we are looking at the element store, so element store, obviously it's a store that stores elements. What we'll see is that each element has a root, right? And these roots, or we call them handle blocks, they are stored in a consistently hashed, persistent hash table, okay, which can be expanded when the system expands and so on. And this root internally, so the root block has some small piece of metadata, but the important thing is that it has pointers to B-trees, or V-trees as we call them, which are persistent B-trees. And then like each element has a 64-bit handle. So generally speaking, we can have a random access. It's not really order of one, but conceptually it's order of one access to the hash table, and then we can traverse the relevant tree. Why do we have more than one trees? So one of the trees can be for like attributes, properties, and the other can be for the actual data. So yes.
I say just B-tree is our research topic. We spend lots of time to research on industry data structure.
Okay.
No question. This is our interesting area.
Yeah, no. So I'm thinking something that would be interesting to you, because I know you've been working with Igor on this. Yeah. Is the V tree is all in SCM, right? It's sitting inside the SCM, so not too far from the persistent memory, and it has this interesting quality that it's concurrent. So a lot of C nodes would be accessing and also modifying the same V tree concurrently. So I know you've been working on graph algorithm in a similar environment. So I think that would be one thing that's an interesting connection for you.
This switch is here is for 3 different disks, right? So they can access
each node here is a block, 4 kilobyte block, and it can be mapped to any of the SCMs in the system.
Oh.
So there is no locality between the blocks. Blocks can be spread like everywhere. That's how it works. And there is like a mapping layer, which given a logical address will tell you which box and which drive you should get the actual block file.
Having to lock. Let's say that based on the distributed file system. That's right.
It's not a file system. It's a distributed system, but it's not a file system. It's at the end of the day, we have drives, which you can look at as block devices that are exposed to the network. So any CNode can access any offset on any of the drives, and then we have like mapping layers, which will tell you, oh, this, so you want this logical address, it's actually here at this offset on this is.
Hi, I have a quick question.
Yeah, it's a variant of a bit, exactly, yes. And the only like special thing, well, couple of special things.
It's pretty special.
Yeah, but but one of the most important things for us is that these things they have very high fan out. So this is a B tree with a fan out of, I don't know, 200, right? So these trees are very shallow. So if we're looking even at a huge file with a lot of metadata, maybe we'll have 6 layers in this tree. And then we don't, on purpose, we decided not to deal with any B epsilon trees or with any caching strategies because the access should be fast enough. So accessing a block on SCM over the network, it can be 50 microseconds, right? And even in the hugest trees, we'll be doing like maybe 6 of these IOs. So that is like, that was our thing. Concurrent transactional, there is an implementation of locks. So each such data structure, it comes with its locks, so it's like self-contained. Locks are also over the fabric, RDMA based. They are stored in SCM. Like the bottom layer, the data itself is stored in Flash, and the CNODs are stateless. We do not cache these things. So I think that's about the architecture. And now let's start diving into the database stuff.
So hi, I'm Mickey. Like I said, I'm going to talk a little bit about how and why we sort data in database tables. And one of the things that you will see, or I will maybe emphasize, is that while the DASE architecture has a lot of very important benefits that Vlad have discussed, when you're doing the software engineering to support it, to use it, it has some challenges. I'm going to mention just a few. One of them is that the CNodes have to be stateless. So we're very used to having some sort of maybe cache on the compute node so that you don't have to access the data all the time. And if you do an update to the data, maybe you update the cache first, right? And you later persist. We can't do any of that. All the states have to be purely on the shared D nodes, which means any C node can be accessed anytime for any piece of data. That's great, but that limits the kind of work that we can do. Because C nodes cannot talk to each other in the architecture, right? A client can access a C node and ask it to do a query. The C node has to do that operation on its own, essentially. That means we have limited resources. For any kind of query that comes in, we are limited in how much resources like memory or compute we can dedicate to that. So we have to be pretty clever. And another issue that will pop up is most software is used to working on a disk. Accessing a piece of data on a disk, given if you know the offset is 12 and you want to access the block at offset 12, that's an O1 operation, right? It's like accessing a piece of data in an array. But as Vlad just explained, everything for us is stored in V trees. Now, these are very shallow trees, like Vlad says, and they're very fast, but still, these things add up, right? So it's not exactly O1. It's more like O log n in some sense. It's very fast O log n, but it's still, you'll see this coming up in many ways on how we work. Okay, so again, if you have questions, you have just stop me. So one thing is that clients come to us and they say, you have a database, we store data on the database. We have a bunch of high volume, a small set of queries that are very, very high profile for us. They make most of our money by running these queries because let's say we're an investment company. and we need to issue queries. And we need these queries. They scan a lot of data. We need them to run very, very, very fast, right? And they scan a lot of data. Let's say it's some kind of range query. So a classic database approach to this problem is to define an index on the query column. An index is some kind of tree or some kind of system that allows you to say, okay, I need to query these nodes or not these nodes. But the problem for us is that the DASE architecture makes indexing not a great idea. One problem is that the C nodes are stateless, so you can't put the index in a cache or do anything like that, right? You have to you can't do anything stateful. The other issue is that indexing generally kind of assume, okay, I'll tell you which offsets of the disks to access. But accessing random offsets on the disk is going to be pretty slow. And you prefer to do sequential access. We're also a very distributed system. So if you put a different part of the index, let's say in different C nodes or something like that, which we cannot even do, even if we did, we would end up accessing the same piece of data by multiple C nodes, right? And that's a waste of system resources. Another issue is that people generally indexes assume that the index itself, even if it's not in memory, it's on disk, you can do random access to get the index. But again, for us, it's not going to be O1 access, it's going to be log n. So here's an example. Suppose we have some data, right? Oof. Let's just do this. Oh, here we go. Suppose we have some data and we want to issue a query, right? And we have two machines, machine A, machine B, two C nodes, right? And the index says, here's that data, and you have to access five rows, right? You have to access these 5 rows marked by arrows, right? And for some reason, you divided the index in such a way that you have row B accessing essentially 1 row in each block, and row A accessing 1 row in 2 blocks, right? So you can see the colors. So if you do the counting, you'll see that some blocks are read by machine B. All blocks, in fact, are read by machine B. Some blocks are read by machine A. And in total, to do this little query of accessing 5 rows, you're going to need to access 5 blocks, right? Again, actually, you're accessing 3 blocks, but some blocks are read twice. So it's an effort on the system. So this is not great for us. So what can we do? Well, we do something that normally people don't do, which is we're going to pre-sort the data on the table, right? Let's assume, for whatever reason, that the table is sorted. How is it sorted? We sorted it, but we'll talk about it later. But let's see the benefits. Let's say the table is sorted, and maybe we're a little lucky because if the data is sorted by the same range as the query, it's going to be one contiguous set of rows, right? So we find a block boundary and we say, okay, hey, you can read the block, the middle block, and machine B can read the rows in the bottom block. And then we just read 2 blocks, a lot less work. And yes.
Question. Right. Yeah. If you sorted that, and then you accessing A firstly, then accessing B, that may introduce some latencies because.
Oh no, it's parallelized, of course.
Parallel.
Yeah, machine A accesses that block and machine B accesses that block at the same time. Yeah.
So that A and B must be in the 2 different disks.
I mean, the blocks are, again, I say blocks, for us, it's something a little else, but they're definitely, well, these are SSDs. Let's start with that. So they have deep queues, right? So it's not actually a big deal. If 2 C nodes accessing different blocks on the same disk, it's not a big deal.
So SSD can support.
Yeah, they have 32 deep. But even if not, actually the way we design our system is that it's actually not going to be an issue.
That's good. Thank you.
Yes.
So how do you find those ones?
Again, I don't want to get into the I can answer it and I will, but we don't actually have what you might refer to as blocks. We have different things. It's a pretty there's a deep stack of abstractions. As far as what we have for the database is something we call a row group, which is, you can think of it as 64K cells, in a database. Now, a cell can be very big or very small, but it's usually not, for us, the difference is not that important. So I don't want to get into all like these things are divided over multiple disks, and it can be as units as small as like, very few bytes, or it can be units that are big as a few megabytes. I just don't want to get into all the details because we can be here like for a month. Okay, so I just wanted to illustrate. So the blocks here are just to illustrate the idea that if we're clever about it, we can avoid accessing the same data twice. That's what I'm saying. Right. So again, people say, okay, so wait, sorting is, a little crazy, right? Because it's n log n. And the answer to that is yes. Sorting is going to be a pain, and most of the talk will be how we actually do this sorting. But the benefit is that if scanning things that are sorted is very, very fast because it's sorted, you know where to find things. It's very easy to parallelize, which is very good in our architecture. We have all these C nodes and all these D nodes. It's very easy to divide the work. And of course, like I said, reading the rows, B, A, B, like the rows on the left, they're not sequential. It's going to be a lot of block reads. Reading sequential rows is so easy. So we get a lot of benefits. And that's one of the examples where I'm going to say, we have an unusual architecture. So it leads us to some unusual choices, like sorting instead of indexing. And we'll see more of that in a bit. So the main question is, how do we sort tables? And that's not something we invented. There's a common approach called log structured merge trees or LSM trees. This is something that is widely used and known. It's usually used in a little bit of a different way. We actually use it to actually sort the data. Usually this is used a little bit differently, but that's fine. We also have our very own, because of the DASE architecture challenges, you'll see, and I'm going to talk about it, how our LSM is kind of different from how, RocksDB works, for example, which is also LSM based. All right. So to explain that, I'm going to talk a little bit about classic LSMs. This is classic tiered LSM. I'm not pretending that this is what people exactly do, but this is variation. Most of what people do today with LSM is a variation on these basic ideas. First of all, whenever you insert, you want to insert it very quickly. So you have an in-memory data structure called memtable, right? And that thing has a lot of very smart data structures, but whenever you have a piece of data, you just insert it to the memtable. And when the memtable is full, or for whatever other reason, you might say, okay, I'm going to take that memtable, I'm going to sort the data in it, and we're going to create a piece of file on the disk, which I'm going to call a run. It's a sorted run. In the run, the data is sorted with some metadata to help me find things. And I'm going to call that tier 0, right? So every time the memtable is full, I'm creating a new tier 0 run. Okay? At some point, I might say, well, I have too many tier 0 runs. I don't want to search a million tier 0 runs. So let's combine a few tier 0 runs. We're going to merge them together, right? Into a tier 1 run, which is just bigger but sorted, right? And maybe I have a tier 2, right? Again, if we have too many rows of tier I, I'm just going to merge them together into TR plus 1 to like a bigger one, right? This is great. And whenever I want to do querying, that's pretty easy. I'm going to check the memtable that has a lot of very smart indexes and data structures for checking, and it's memory. So it's very easy. And then if it's not in the memtable, I'm going to just search the sorted runs. This is fairly easy because they're sorted, so I can just do something like binary search, right? There's a lot of optimizations that real systems use, including things like Bloom filters to detect cases where the data is not in the run or it's not even in the entire table without actually having to do the search. They use things like data sharding, where they say, rows 1 to 1 million are on this machine, and rows 1 million to 2 million are on that machine, right? Vlad mentioned sharding before, and that's what a lot of these systems, high performance systems, do. They use sharding to divide data to different machines. Okay, but we are in VastData, and we can't do many of those things. So first of all, An in-memory mem table is going to be a huge deal for me because I'm just going to do something because I don't have the clock here. Great. So I can't do an in-memory mem table because I can't just take a C node and put it there, right? It has to be shared. So no. Second, we have a flash-based system and we have a high-performance system and people insert a lot of data into it. So we don't want to have a lot of write amplification. If you look at the way classic tiering works, you put data into the mem table, you write it once to tier 0, then you write it again to tier 1, then you write it again to tier 2. A lot of write amplification results in this, and we would prefer to reduce that. Another issue we have is that at the last tier, the runs are like so big, and we don't like having big objects because it's hard to operate on them quickly. They're too big. Other issues is we want to limit the amount of runs that we need to search. We can't use Bloom filters, in-memory Bloom filters, for the same reason why we can't have a real mem table. It's in memory. And that means state per C node, we can't do that, right? Because one C node will never know what another C node does. So if you insert a piece of data and you haven't updated the Bloom filter at every C node, you will never know. We can't do that. We have a lot of C nodes. All right. And like I said, sharding. No, a client can talk to any C node to get any piece of data. That means we can't just say this C node is in charge of these rows and this C node is in charge of those rows, right? So a lot of these classic solutions are not going to work for us. So I'm going to talk a little bit, again, if I can get this. Yes, of course.
Is that no, next one? Next one is
This one?
yeah, these are the node in memory meta table. So the meta table is on the disk.
Yeah, so there's a cache usually, and there's Bloom filter also that there's in memory. So mem table sometimes on the disk. It should be on the disk, but usually, as I understand it, usually you write to the mem table, but what's on the disk is a log, right? But you still use the mem table. The log is just for persistence, if I understand, right? But when you do a query, you search the memory. It's still in memory. But it's true that there are, like I said, this is a very, like, if you look at the classic version, this is just a classic. People, even if you put it on the disk, it assumes O1 access, which we can't do. So yeah, we can't actually have a mem table. Let's just say that. Yes.
Yeah, so the mem table improved the complexity from n log n to log n, right?
So the mem table, again, I'm not an LSM expert. So I don't know if that's what reduces the complexity. What I do know is that when you do a query, it's O log n to search every run, right? And if you do it correctly, the number of runs is also not too big. So you get like essentially an O log n search.
It should not improve the worst case. I think it's improve the average case.
It definitely improves the average case, yes. And there's also which I understand that, again, I'm not an LSM expert, but I do understand that one of the things you want to do is search the runs from the tier 0 first, and then tier 1, and then tier 2. Again, I'm not an expert, but it's, it doesn't matter. We couldn't build it, right? For many other reasons. But that's a good point. Like, this is not a class about LSMs. This is just very basic ideas. All right. So what we want at VAST is, first of all, we want to still maintain sort of logarithmic search time, at least per run. We want to reduce the write amplification, like I said, because of the reducing flash wear and because we want to have good performance. I mentioned that we want to avoid large runs. And one of the reasons is that it's much nicer for us if we can do things like merging and sorting runs, database internal operations, in the context of a single transaction. And we don't want to have very long transactions, which means we can't have very big runs. There are other issues about, if the run is small, then the V tree for that run is relatively small. Again, I don't want to get into all of that. Other things we want is we want to make sure that all IO is sequential. This is not something that's unique to VAST, but what's unique to Vast is that if we can do sequential I/O, we can gain huge performance benefits, and we just don't want to give that up, right? So as far as we're concerned, if we do random I/O, it's way worse than when. Here we go. I'll do a share.
Alright.
Yeah. Everything okay? Vlad, אתה רוצה את הטלפון שלי?
No.
Okay. Yeah, so we're back. How are we going to achieve these goals? I'm just going to talk about three things. A little bit about the system architecture, a little bit about how our density-based LSM works, which is unusual. It's not like the novel one. And how we kind of put data from the database directly into the storage layer, right? Which is something normally you can't go to like an SSD and say, please put some data in there. But we have full control, so we can do this. All right. So, of course, we don't have a mem table. What we do have is what we call a landing table. This is a completely standard vast database table. It's just a table in the database for which whenever new rows come in, when a user inserts rows to the database, we just put them there. Okay? Just one after the other. Because it's a vast database table, it enjoys several things. There's full transactionality. It's ACID compliant. It's persistent. It's very high bandwidth. It's very, very high performance, even for querying, as long as you don't make it too big. So that's great. So that avoids the need for a mem table to like all the ingest. No problem. We just put it in there. We don't need a separate mem table in a log because we just put everything into the database. So all the writes go into the database. Okay. Then there is something called a sorter that's going to basically read the rows from the landing table, sort them in memory. It's going to not read all the rows. It's going to read about 500,000 rows. It's going to sort them in memory. It's going to create a sorted run, what we saw before, right? It's going to register that run in a different sort of metadata table we call the index, and it's going to delete the rows from the landing table because now these rows sit in the run. They no longer sit in the landing table. And this means that the sorter is the thing that makes sure that the landing table is not inflated, right? It keeps the size. There's a merger. It's an LSM. You need something to read, let's say 8 runs, merge them together, and write 8 new runs that are now sorted in a better way, right? And whenever a query comes in, you're going to need to query the landing table. You're going to need to look at the index table, the metadata, to know which runs are relevant to that query. And then you're going to search for the data in those runs. Again, in kind of the same way an LSM works, right? But one of the nice things about it is that we can very highly parallelize that query. We know exactly what we need to read. We kind of know how many rows and from where to get them, how many rows in the landing table. So we can divide the work very efficiently and parallelize it over a lot of cores. I want you to notice, and that's all I'm going to say about the software architecture, because this is nothing too special. This is not uncommon, but it makes like this design means that every I/O in the system is parallelizable. It's sequential, which is what we wanted to do. It's transactional, and it's also isolated in a way for ingest, sorter cannot interfere with merger. They're all easy to isolate. It's not that they don't always interfere. There are cases where they could interfere, but even then, it's very easy to reason about what's more important. Okay. So let's talk a little bit about our LSM. So the first thing we did with the LSM is that we limited the maximum run size. Classic LSMs also do this, but they use much bigger SS tables. We limit the run size to about 10 million rows. And if we are merging a lot of, 4 runs, 10 million each, we get 40 million. Instead of having one output, which is a sorted run of 40 million, we just get 4 of those runs, right? You can see it in this picture. It's a nice 10 million is a nice sweet spot for us in terms of the size of the V tree, in terms of how many runs we can merge in a single transaction, how much memory we need to sort those runs, and so on. And it's 10 million is still fast enough to benefit from log n searching, right? If you're not gonna get any benefit if the run is like 1,000 rows. And obviously, if you could have 1 trillion runs, sorted data of 1 trillion, you would get a lot of benefit from the binary search. 10 million is pretty much a sweet spot for us. Okay, so that's number one. Another thing that we're doing is that's not something we do, that's just something that happens. If you take a run and you split it after the sort, what you're essentially doing is you're taking the key space, which previously, let's say, was from 0 to 1,000. And when you initially had runs that cover the entire key space, if you're going to merge them, sort them together, and then divide it again, you're essentially partitioning the key space, right? Because the run will not start at 0 and 1,000, maybe 0 to 200, and 200 to 250, and 250 to 800, and 800 to 1,000 again, right? You essentially split it. How do you split it? Based on the data, right? We don't try to partition the key space on purpose. It's just something that happens, but it will help us. And that's because what it means is that we now have the concept of density. The more tiers, the more times you sort a run, the more dense the data. What do I mean by density? Think about the runs at tier 0. You got a bunch of data that the user inserts. It covers the entire key space, right? From 0 to 1,000. And it has 10 million rows, let's say, right? Okay, that's, if you look at how much of that key space those 10 million rows cover, that's some kind of density. Once you merge those runs, right, and you split them apart, now suddenly the key space is a quarter of that, right? So we say the run is more dense, right? More keys, right? Sorry, fewer keys for each row. Rows kind of cover less of the key space. So we say, okay, the higher the tier is, the more times I sorted the data, the more dense the run is, right? And in reality, the key space is determined, again, not because we said this is the partitioning, but it's based on what is the data in the run. So the run covers different parts of the key space. So you may end up with some runs being more dense and some runs being less dense. And that's normal, right? But the key issue for us is we use that density to make decisions about how to merge things. So here's where we differ bigly from other classic LSMs. Our decision of which ones we're going to merge are based on 2 things. How dense they are, based on the data that they have, not based on any kind of static partitioning, how dense they are, and whether the runs overlap. Because it makes more sense for me if a lot of runs are basically covering the same key space, let's merge them and then sort them and make them even more dense. So what we do is during the merge, whenever we create a run, we compute some quantiles, essentially a histogram of the keys, right? So during the merge, we load those histograms. We build like a giant CDF for the entire key space of the entire table. It's approximate, of course, but it's good enough. Using the CDF, I can get any run and essentially compute the density. This means one of the benefits of this is that it means runs that were generated, if a user gave me data, that resulted in a high density run, I don't need to sort it 1,000,000 times. I already know that run has a high density. It already covers a small part of the key space. I don't need to think about it so much. Okay, so then once I know the density for all the runs and I know how well they overlap, I basically choose among the runs with the lowest density that have the highest overlap. Let's say these blue runs, right? And I'm going to merge them together. Next, I'm going to take the next group of runs with the next density. Let's say these medium density runs. They all overlap in the key space. So I'm going to merge them together and then divide them. The result is I keep increasing the density of the runs. The runs cover fewer and fewer key spaces. So this comes with a lot of benefits. Like I said, lower write amplification because dense runs just bypass the whole sorting thing. Second, we can directly minimize the overlap. And the overlap is very important because whenever we get a query, we have to search all the runs that overlap the range of the query. If I'm looking for a key, I have to search all the runs that may contain that key. So minimizing the overlap is an important goal for me. In our approach, we directly optimize the two things that mean the most for us. The density, we keep increasing it, and the range, the overlap, which we can actually limit. We can say, don't stop merging until the overlap is, let's say, 7, right? We can keep merging until it's what we want. There are other things. This is very adaptable. If the user changes the key distribution, the system will naturally adapt because it computes it on the fly. It avoids inefficient merges. We don't try to merge. If you merge a low density run with a high density run, the result will not be very good. I'm not going to get into that. Let's talk instead about querying. So for querying, basically, I need to query the runs that overlap the key space. So let's say the query range is so-and-so. I look at which runs touch that key space. I know this because that's why I have the index table. So it's very easy to find. And then I scan them with a binary search. Let's talk about binary search. Classic LSM, the runs are stored on disk, right? Disk access is 01, so I just do a log n binary search, easy to find, no problem. Vast DataStore, the runs are stored based on a V tree. To access a particular offset in the run, I need to search the V tree to find which block it is, right? That's we have quick V trees, it's quick. But again, if you multiply it by multiple accesses, even something that's 50 microseconds, if you do it 20 times, it becomes a millisecond, right? You don't want to do that. So and if you look at the algorithmically, it's you turn something that was all log n, you have log n accesses, each access is log n, so now it's log squared n. Not great. Here's something that's nice. We can do this. If a run is sorted, then a V tree can be used as we can replace the binary search with a V tree search because it's a V tree is sorting the run by offsets, but the run is also sorted by data anyway. So it's the same sort order. So all I have to do this is to embed some information about the keys into the V tree in addition to the usual information about the offset. And now I've replaced multiple tree accesses to do a binary search with a single tree search in O log n. And I can do that only because I have full control. I can just go to the V tree and say, please store that information in every node. That is something that we have control over. It's another great example about how our design is both giving us challenges, but then it's like the solutions come in, right? Okay. This topic we won't have time for, I believe, which is how we do one thing. I'm just going to cover the idea. Okay. Oh, by the way, again, if there are any questions, I'm happy to answer. No?
No.
Not now.
All
right. So let's talk a little bit about multiple sorting orders. I'm not going to cover this. We don't have time. But here's the idea. So those clients that came to us and said we have high profile query, they come to us and say, actually, we have several high profile queries, and they're not all coming with the same order. So what we want is one table with multiple sorting orders. Or what they actually say is we have queries. Some queries are ordered by date or date and price. Some queries are ordered by client ID. Some queries are ordered by manufacturer ID, right? We want to create a projection of the data that is sorted by that order, right? So that you have one table with multiple sorting orders, but it's still like logically one table. By that, I mean, it's a single table, which means whenever the client inserts data, they only insert it once. They don't create multiple copies in that sense. They insert the data once, and all these projections are always consistent with each other and with the table. So if I go and delete data in the table or update the data, all these different ordered projections are the same. So it is a projection of the data. It's not multiple sorted tables, and that's important. But, and here's a huge difference, unlike a classic database will solve that problem very easily by creating multiple indexes, right? You index on the data and the price, and then you create a different index for the client ID and the price, and manufacturer ID, you just add indexes for more queries, right? The problem with that is that the more indexes you add in a database, the slower inserts become, because you have to update. Not with us. We want to create all these projections without impacting insert performance. When I insert rows to a table that has 10 sorting orders or one sorting order or no sorting order, should be the same high performance. So we still are benefiting from the sorting. We're not delaying the inserts, and we are avoiding random reads. So I'm really not going to cover all the issues with this. I'm just going to list some of the issues with this. One issue is that, as I said, these projections have to be consistent with each other. That means that you have to propagate deletes and updates. But the main issue with that is that when you delete data, let's say, which is ordered by date, you go to the date projection and you say, select everything that happens between this date and that date. So in the date projection, this data is sorted by date. So it's like sequential, right? But if you then say, okay, well, now I have to delete the rows in the projection that is sorted by client ID, you've just turned something that was sequential to something that is now essentially random, right? Because the client's ID have not ordered by date. So everything now becomes random access by definition, right? That's hard. And that's in fact most of what today's lecture we spent a lot of time working on that. I'm not going to cover. We have performance models and a lot of clever scanning algorithms and more performance models, and it's a pain. Not covering that. I'm just going to say we fixed it. If I wish, maybe another time I'll come and we'll explain just that.
I hope next time, next year.
Yeah. Another thing that is a challenge is tracking. If you only have a table that's sorted by one order, you can go to the landing table, pick up a bunch of rows, right? Sort them, put them in the run, and delete them, right? But if you have multiple sorting orders, it's hard. You need to keep track of which rows have been sorted, and not just which rows have been sorted, rows have been sorted to which projection, right? That we solved that using Laporte clocks. Leslie Laporte knew what he was doing, and he invented Laporte clocks, and that's what we did, logical clocks. There's an issue of how do you select the best projections for each query. Again, we have solutions and even better solutions. How do you create a new projection? Again, Laporte clocks. There's a complicated system that allows rows between different projections to locate the equivalent row in another projection. You have projection X, you found a row, right? You want to allocate that same row in projection Y because maybe you need to delete it, right? So there's a complicated systems of, we call them pointers, that kind of point between all the rows. Pretty complicated because we have to do it in a way that's fast. You have to do it in a way that's not increasing the data size too much, all kinds of things. Again, not going to talk about that. Instead, just a little bit about some of the challenges that we kind of foresee in the next future. If we come again next year, it might be something completely different. Maybe we'll say, oh, we already done that. things move fast. One thing is, again, we talked about Bloom filters before, right? The idea that maybe I have a probabilistic data structure that for a given set of keys tell me these keys are in the table, or these keys are not even in this run, don't bother searching it, right? There's all kinds of papers. There's a recent one we've been talking to the authors on range filters, queries, and things like that. So in classic LSMs, you do have a Bloom filter. You can put it on disk, you can put it on memory. They usually put it in memory, where basically it's easy to check, it's easy to do. It's a small data structure that they use ribbon filters in RocksDB that can just tell you, yeah, it makes sense for me. It's such a O1 disk access to figure out if the disk, it's much better than O log n disk access to do a search. So yes, let's put a Bloom filter. But for VastData, turns out that the performance model, the performance characteristics of the system are completely different. And because we have to store the filter on disk access is all log n. It's fast all log n, but still. And interestingly, on classic filtering, they kind of assume if you want to access a filter, it's O1 access. But if you want to search a run, it's slow all log n binary search. For VastData, both things are different. To access the filter bit, it's log n, fast log n. Turns out because of what I explained about how we make the searching of a run into a tree search in Vast, then searching a run takes as much time as finding the bit of the filter. There's no point, right? I'm not gaining anything. It takes me the doing a false positive is just as fast as just querying the filter, right? So this is interesting. Searching 50 runs, even if it's the filter, even if I will only find a point in one of them, and even if the Bloom filter is perfect, and it would have prevented 49 of those searches, searching 50 runs is still faster in our system, because the search is embedded in the V tree anyway. So we don't do binary search. Again, but that's not the end of the story. You can develop filters with different performance presumptions. We did cost models that say if we can group, let's say, 10 runs with the same filters in some way, which is not easy, then maybe it's worth it, right? So that's something we're looking at. We have a lot of challenges in the vector index. One of them is vector indexes. Our vector index works by resorting, continuously reclustering the data and moving things around. And we needed a way to find vectors by some kind of key. So again, we developed this kind of versioned index where you can search by a key and use the maximum version, and updates become sequential because you don't have to update individual rows. You can just insert a new version of the same key. Again, I'm not going to go into it, but again, there comes a lot of challenges. We have a lot of systems challenges, like end-to-end encryption. Today, the client is sending raw data to a C node. The C node is writing raw data to the buffer, and then another maybe C node comes in, reads that data, compresses it, and writes it back. If the client could send the data compressed when inserting rows from the beginning, we could do a much higher throughput, essentially, right? So that's something that someone's working on right now. And that's pretty much the end, right? Because I don't want to, we've been speaking for quite a bit, but again, for me, the takeaways is that there's a lot of benefit from the DASE architecture in terms of scalability, resilience, and so on. But because it carries different assumptions, that means we get to revisit classic database, classic system design, right? Indexing, no, we sort. Tiered-based LSM, no, we need a density-based LSM. Binary search, no, we just put things in the V tree. Bloom filters, no, just search. And again, multiple indexes become multiple LSMs, all kinds of these issues that are interesting. Maybe, and that's it pretty much for me. We might want to say something about yeah.
So as we mentioned, the R&D center, we have an R&D center in the Toronto area, and we are focusing on basically more or less what we presented. core distributed database internals development. And there are like conceptual impression, partition secondary indexes. We'll also be getting into the vector similarity search indexes as well. And the way that we work, so the group is growing, but we're still a relatively small group here in Canada. And the cool thing about it is that we take large, important, complex features and we deliver them end to end. So we start from the very high level concept, you can call it like architecture level, and we do the whole cycle of doing the design, the implementation, and testing, performance, tuning, debugging, and then delivers with customers. So in a sense, we operate very close to what you would call a startup, even though the company is not a startup. It's a medium-sized company, but the group operates in this manner, which I think is pretty exciting. And we are hiring. So.
All right. So thank you very much for your time. If you have, like, we're here. If you have any questions, we can have a discussion.
Where's the location? This is the Toronto center.
So we have an office in Vaughan.
Wow. Okay.
It's near Toronto. Yeah.
It's near to here.
And if you have any questions, so discuss now. Feel free to reach to me or Mickey.
Von Ben has our email, so for sure, or you can take a photo. I don't know. But yeah, and again, happy to answer any questions, or actually also maybe hear about some of the stuff you've been doing, because I think
you were at least when at the database conference, remember you mentioned how some of your systems at least had persistent memory in mind. Usually
you come back?
Yeah.
Okay.
Yeah. How they used persistent memory, or at least you had persistent memory stuff in mind. What the happen?
The SCM that Vlad mentioned.
Yeah.
So that's the one, and Vlad can honestly. Vlad knows everything about the company because he's been working here for 9 years. I can only give you general, so he can give you specifics. So I'll let him answer.
I guess from my understanding, you're trying to replicate persistent ability, or at least is it like replicated functionality, or is it like actually in your system per se? Or is like I guess the idea of it, the function of it is like simulated, I should say, if that makes sense.
Can you refine your question?
Oh yeah, but I guess in terms of like performance, like access latency times, like thinking about like the whole memory hierarchy, is it was SCM you said, right?
It's first class memory.
Yeah.
And it was something else before, right? It was actual Optane initially.
So SCM is a generic term.